Okay, I guess so. In the beginning, I will say a couple of things about hot. So, fortunately, I guess most of you know this already, but I think it makes sense to. Oh, yeah. Maybe I'm boring a few of you. That's what I'm going to say, but don't worry. Yes. Later on, that's stuff that's probably interesting for everyone. Yeah, but I think we should try to bridge the gap a bit. So let's start with some remarks. Multiple-type theory. So by now we have really used like higher types, but I still want to like give a definition of n-type. So for n actually starting at -2, for historical reasons, I guess. The type x is n-type if, and now we make a case distinction. So for the case n equals 2, then we just want that x is the one-point type, or as it usually is called in multiple types theory, we define triple type is control, which says that something is contractible in a very topological sense. And yeah, but that's enough. And for n greater -2, we can make a recursive definition where we say for all x, y, and x, the identity type is an n-1 type. And what we freely use so far is, in a couple of places, is that we have a universal way of turning a type into an n-type for each n. So for the first one, it's really just giving a map to this terminal type, so to say, and starting from that, it gets more interesting. So that's just some fact. It's a construction which you can look up in the hot book or somewhere else in multiple type theory, which says so there is a construction with a map on types called n-truncation, which has following universal property. It actually has more, but I want to write it in a way where it is kind of the same as that of a reflector in category theory. So for all things in the subcategory, so to say, which are now n-types. So for all y, n-type, and for all maps like this, you have a union here. And you actually have a bit more. So, so one way to say what you have would be to rephrase this in a way where it is about dependent types, but I think with this you get very far and you can do everything we do, more or less, I think. So I'll just leave it at that. And also for context, so this is well, is So to the datum, there actually also belongs this map, but that's okay. So there's a modality, and the sheetification Thierry mentioned earlier is also an example of a modality, but one which is also left exact. So it preserves even more structure, but what Thierry mentioned was that the sheaves are stable under all type formers like identity and pi and sigma and so on. And this is something you already have for a modality. And then the laxness is that it preserves fullbacks. So kind of a small addition on top, because modalities even preserve already quite a lot of fullbacks without the extra laxness. So this is also like a reflector, which is already close to being like a sheafification, but not completely. So just lacking preservation of some fullbacks. Okay, and we've seen examples of one types, by the way. So this G that appeared a couple of times is a one type. The schemes we saw are all zero types, and the propositions are -1 types. And there's this convention which we already used a lot, that the -1 truncation, which is also called the propositional truncation, is kind of the default index. You write nothing. Okay, so now I want to be a bit more specific. So, no, I still have a couple of general things I want to say. So this is the definition or a reminder of notation. So X. So we will talk a lot about pointed types now, and it just means that, well, you have a type and some fixed element, which I will always call star. This pointed type. And I will kind of always just say it's a pointed type, but not write this pair. And written X. So kind of, if we say something is a pointed type, we always assume there's some element called star, like no matter in which pointed type it is. Okay, and a pointed type X is connected means the definition for all X in X. X equals the star, but only propositionally truncated. So if I drop the propositional truncation, it would already be contractible and equal to the 1 point thing. So that would be boring. And this is a way to say something like, if you view types as screw points, or you see an analogy to topological spaces, this is how you can say topologically connected without making it trivial by propositionally truncating here. And what else do I want to mention? Yeah, okay. Very important in the following, let X be pointed type. Then we can make this definition. Omega X, the root space of X, is just the one identity type we can universally form. And yeah, this is called loop space. Okay, and it turns out if you have X pointed one type, then X is a group. So you have these rules for identity types, which are kind of transitivity and symmetry as operations, which means you can put equalities together, so compose, like concatenating pairs in space, and you can switch them around, which is like the inversion in the group. So you have a group structure on this group space. And now one interesting question is, when can you reverse this? And for a group, you can always, in order to construct a type such that the loop space of this type will be the group again, with its group structure. And if your group is abelian, and that's a fact we will use a lot now, so let A be an abelian group, then say it's precisely and a natural number, then there is a type K(n) called, so I guess this is something I could write readable in case someone wants to look it up. So I guess it's easy to find constructions of this in hot by googling this. And what we have, so I mean, first, the property I stated is if you say n is 1, you want some type such that looping it gives you back the group with its structure. So I make a very redundant list here and start with this thing I use as a teaser. Like if you loop it, you get an isomorphism with a given group. So that's what we are most interested in here. And you have a couple of other things. So first of all, if n is greater than 0, so I mean, this is like the special case. I just want to include more for one reason. So for 0, you just want A, but starting from level 1, where it gets interesting, we want that it is a pointed connected type. And what we also want is that KAN is an n-type. And like the higher ones should just be iterated deloopings. So KAN looped would be KAN minus 1. And I don't want to go into details here too much. I think the way to put all of this and construct it I like the most is written by David. So I guess if you Google this and his name and what, that should be visible somewhere. And there you can also phrase this as some isomorphism of some structures, but I guess, yeah, let's not go into details too far. And I mean, yeah, if you know this, I could have kind of dropped the n-type, because then with general laws, so the truncations, we have well-lived deloopings, and you can commute stuff a bit. So you could already conclude this has to be an n-type if at level 1 you get 0 type when you deloop. Okay. And yeah, now we kind of already move a bit towards cohomology with the next remark. So, yeah, maybe this is a bit unmotivated, but it turns out it's very interesting to look at maps from a type into these Algebraic-MacLane spaces. And I'm doing things now a bit like the other way around than they appeared historically. I mean, first, those spaces appeared in algebraic topology, where people maybe ask the question, I'm not entirely sure how they came up with it, but that's at least how I learned it in my algebraic topology course, that if you look at cohomology, like singular, is it called? Singular cohomology in algebraic topology, then you can figure out that it's possible to represent cohomology as maps or homotopy classes of maps between topological spaces. And the spaces you need to represent cohomology with coefficients in some group A are these Algebraic-MacLane spaces. And here we can kind of turn this thing around and define cohomology using these spaces. And the kind of interesting thing is that this seems to be a lot more fundamental than the singular cohomology, which is kind of more specific to algebraic topology. And yeah, and one important point is also that there can be some confusion, because in algebraic topology you talk about maps between topological spaces, and if you transfer this to Hot, you might think we can only use this for the groupoids, like on the level of groupoids, that the groupoid structure, like the higher type structure on two types, is what corresponds to the picture from algebraic topology. But that is actually wrong. So it's more fundamental. And you can also have interesting maps from a zero type into an Algebraic-MacLane space, and also define interesting cohomology for zero types using this algebraic topology idea. And that's, I think, a bit a surprising point. And I mean, one picture I use to rationalize that this is actually interesting is that, for example, Ka1, you can kind of imagine as some co-limit. So one way to see it as a co-limit is to say you have your group acting on a point, and now you take the homotopy quotient of this group action, then you get the point with self-identifications for any group element. So in this way, it's a self-identified thing. So it's identified with itself a point in many ways. So it's like some co-limit. And when you look at maps from some zero type into this, you kind of compare identifications that happened to build this space with this identifications of this point. So when you write down like the universal property for homotopy push-out, and the zero type can be a homotopy push-out, then you can kind of see that equalities in this space you map into appear in the mapping out principle from the push-out. So yeah, but I mean, that's just a way to rationalize it. And if I have time in cohomology 2, I will make some incarnation of this precise, which is called the Meyer-Vittorius sequence. But yeah, let's just go on with some facts about what happens if you map into something, yeah, or maybe this is a remark. Yeah, so first something basic. If you have y pointed, then you can look at this thing and it will be pointed again. because you have the mapping all elements of X to this point. So it's just a constant map. So it's automatically pointed again, and we can loop it. And now you could ask, how does it correspond to maybe looping Y just? And the answer is the correspondence is as easy as you might guess, and that's just function extensionality. So if you have that in your type theory, you kind of have this. And but if you look how it behaves with Eilenberg-MacLane spaces, it gets complicated, as it should be. Otherwise, this cohomology idea would be, yeah, maybe this is a warning triangle. So if you have a group and some type, you can look at maps from X into this group, and it's a group again. And just by pointwise structure, so you can ask what happens if I de-loop this, or if I build the Eilenberg-MacLane spaces. And this will, in general, so sometimes it is, but in general, this is not the same as doing it the other way around. And it's very interesting to look at the failure, like what the difference is. Okay, and one other detail, which doesn't really fit, but which is good to know here, is if you have a group which is a double loop space, so GQ, and this is an isomorphism, then the abelian. This is also not too hard, I guess. I don't remember called Ekman-Hilton argument, but yeah, it shouldn't be hard. Okay. Yeah, so where did I go from here? Yeah, good. Now I can define cohomology. So this is the end of the remarks on hop. So now we can go back to SAG and make the following definition. So let X be a type. I mean, it will later be kind of always a scheme, but we don't have to restrict us to schemes, and it's interesting to see it for other types sometime. So let X be a type, and these are the coefficients, and they are given not by a single abelian group, but by a map to the type of abelian groups. So the coefficient we take, which is a bit unusual when you come from an algebraic topology direction, I guess, is that you can freely vary your coefficient with the place you are at in your space. So, yeah, and n is a natural number. Then Hn of X with coefficients in n is these interesting things up here, but now written as a dependent type. So we kind of take the dependent version of this one, and then 0 truncate. So, I mean, I guess we used pi, but alternative writing is this. And I guess I will use both. And yeah, if this is constant, then we just have this mapping type from above. Okay. And so we can make a couple of remarks. So because this is just a type of maps, we can easily deduce a lot of things. So Hn is functorial in both arguments. And I mean, what you do to see something like this, if you kind of new to it, is you first do it on the level of the inner stuff, and later you can use this principle to get it for the truncated things. And actually, what is a bit different also from usual algebraic geometry, I would say later, is that you work a lot directly with this type in here, which is sometimes very convenient because you just have a pi type, and it's a very basic thing. So it's good to just work on that level a lot. And this is a Abelian group. And you might wonder what about ring structure or modules and so on. So far we haven't actually explored anything in that direction, not because it's there's something blocking so on. So you could like also say if you have module coefficients, you get a module structure here. But for now, we plug in modules later, but we just forget the module structure. But yeah, I think it should just work to also get a module structure on this one. We just didn't have a reason to do so far, or to look into it. Okay, so yeah. Okay. Yeah, so this is something I will more show later. Yeah. You can show a lot of theorems about cohomology defined in this way, just using hot, without anything specific to algebraic geometry. And the main, so this is also something like people knew for a long time that we could just do this. For algebraic geometry, synthetically, there were two main questions. Like, for example, what should we use as coefficients? And how do we prove cohomology is zero, like on anything of interest? So in algebraic geometry, classically, you have the theorem that higher cohomology with values in OX, quadruple OX modules, vanishes on an affine scheme. And this is something you need to get started to compute any other cohomology with values in OX modules. And so the question was, can we show basic theorems like Hn on something affine vanishes? And to be able to do this, we invented the Zariski local choice axiom, because without that, I think you just can't show it. But I mean, I don't have a proof that it's impossible with the other two axioms, but it seems quite unlikely. Okay, so let's look into like basic proof that shows triviality on something affine. So I kind of artificially restrict it a bit to eliminate noise. And I will later tell you in what generality it actually is known to hold. So that A, the finitely presented R algebra, then H1 of spec A with coefficients in the base ring R vanishes. So this is the choice we came up, that this is actually a reasonable replacement for the structure sheaf. So you might note here that in classic algebraic geometry, the structure sheaf isn't constant. So here I have a constant coefficient, but the point is that this is a non-constant sheaf. So the coefficients you usually use in classic algebraic geometry are something like something that can't be a non-constant sheaf in the Zariski topos, because that's not the kind of object you put in. So you put in something completely different. And in the beginning, I actually tried to reproduce like the structure sheaf internally, but yeah, that's just horrible. But I guess it could still be interesting at some point to compare. But I mean, that one works wonderful. So let's just go on with this. But I mean, for me at least, it wasn't clear that this is a good choice of the coefficient. Okay, so we defined this as a zero truncation. So now it's a bit low. So we defined it as a zero truncation of some mapping space, and we say it's zero. That means it's the one-point type after we apply the zero truncation. And if you like commute identity type forming with truncation in the right way, that just means that this claim follows from, or is actually equivalent to, that this inner thing without the truncation is a connected type. So spec A2, and now I have to apply this one, and I'm back in a plane space is connected. And so to prove that this is connected, so connected means everything is truncated, propositional truncated, equal to the trivial thing in here, which is the mapping everything to point. Just means that we have to take some arbitrary element, phi, which goes from spec A to K1. And we need to show I is equal to the constant map. So this thing. But only nearly. Okay, and we said that this space is already connected. So this is something which we have at each point in the codomain. So by connectedness of AR1, we have for all the x in spec A, merely I of x equals star. So what we want to do at this point is kind of move out this truncation, and the Zariski local choice axiom is what allows us to do this, but on a cover. We have to pass to a cover, it's outside. So Yeah, okay, so we move the truncation outside and pass through cover. So there is the local choice. Right, so that one gives us elements which give us the cover. So they are covering, yeah, no, the algebraic way. And on each part of the cover, we have some proof of triviality of our type. So for all I, we have some SI, which goes from EI to prove, so we use a dependent function here, to prove that IX is trivial. And now maybe you notice I'm kind of dropping the propositional truncation. This is like just because in the end we will prove a proposition. We want to prove this is propositional truncated. So here we can allow ourselves to forget about propositional truncations if we want to use this stuff, those assumptions to later prove this thing. Okay. You cannot in general forget all propositional truncations in a proof where you prove a proposition in the end. So that's not what I want to say. Okay. We have this, and so now we have like a cover of our space, and on each piece we have a trivialization. And our task now is to piece these things together, which doesn't work as they are, probably. So it could be they are just incompatible. And our task is to find some correction to make them fit together, to glue them together to some big S on all of spec A. Okay, so how can we do this? First, we look at the differences on intersections of our cover where they don't agree. So a difference like this can be defined by writing this. For each X in the intersection of two pieces of the cover, which is just the D of the product, which is important because by duality, that means everything takes place in a ring which is a one-element localization. So that means I have defined a function Tij, which goes from this Fi to R. So by duality, I can also view it as some element in this algebra. Okay, but it's not just that I have a random selection of elements in these algebras, but they fulfill some condition due to the way they are defined. So I have that whenever I have three indices, maybe this ijk, then I have what is called a Cohomology condition, which means this is zero, which we can just see on the level of functions by the definition here by expanding, because a couple of terms cancel out, and in the end you just have zero. Yeah.
So did you define this action, this J, this line.
Ah, okay. Yeah, maybe I should say a word about what I mean with minus here. Thank you, Terry. So the values here are in this type. So it's not so clear what minus means, or not clear at all. So Sj of x is something from of this type, and maybe it's too small. Oh, I don't know. So, right, bigger. So this means I take how do I actually want to do it? Good point. So, okay, so this is like this.
But we have a torso over a group, and so
yes, but we didn't talk about torsors. That's why I don't
use there.
Yeah, but I want to do it in a way which is compatible with what I said before. Yeah, but otherwise, yes, you can just say we have a torsor and then what the difference is. Yeah, for people who know what a torsor is, or to make a torsor of that. Yeah, but to take a difference like this, we can use concatenation of pairs and inversion of pairs. So I want an element in R in the end, so I should get something of type star equals star. So that means to do the minus, I should actually do something like this to the -1 times this. So from the types that fits now. I mean, I first turn this around, I go from star to chi-x, and then with this one back from chi-x to star. But yeah, if I say it like this, it's a bit weird to call it minus, but yeah. Good. Okay. So yeah, in any case, we have this relation I wrote down. So Tjk minus Lk plus Lk equals 0. And at this point, we have something purely taking place in algebra. And there you can just make a calculation which gives you the correction factor. And so let me just give you some idea how this works. I mean, to carry it out, it's actually like a good exercise if you want to do like some algebra, but I don't know how much sense it makes to carry it out on a board. So I also have to look up the term. And yeah, so I mean, first you can assume by changing a couple of things that, and I think that's also something you should do when you want to solve it in a kind of pleasant way, that your Tij are fractions like this. I mean, a general element here is some element of, I shouldn't call it R, but rather A, I guess. Or N. Yeah. So a general element here is something in A divided by a power of this. And you can rearrange stuff a bit so that it looks like this. Maybe. Yeah, but that's not so important. And then you can transform also by multiplying this thing here, this cocycle condition, to something which which looks like this. Okay. And you have some factors here. So this is J, this is, no, that's JK. So this is J, this is J. So it's like some symmetric thing going on in indices. So you transfer this equation like this. And then, a bit surprisingly, you can just write down what the correction factor is. So it's kind of a very constructive calculation. So you just write it down like this. And okay. Yeah, I was wondering about that one. So how should I call this? AK, I guess. So so this is Fi and MIK. And so this AK is from a condition we haven't used yet, namely that we actually have a cover, which is important, otherwise it doesn't work. So having a cover means we have a linear combination in A, which gives us 1. So we have a finite sum like this, and we need these factors. And now you just use this and calculate, you should get the result, which is that Tij can be expressed as differences of ui's. So you get Tij equals uj minus ui. And there's a lot of type coercions here. I mean, you go from some one element localization, which you have worked on here, to the localization with respect to this. But yeah, so you have this equation. And you might have seen this already in algebraic geometry when you learn that the check complex for some cover like this on an affine scheme is exact at position 1, I guess, depending plus modulo index errors. And yeah, this is exactly this kind of exactness. So this is yeah, like in the kernel of some boundary operator, and this tells you it's in the image. Okay, yeah, but then in algebra you can calculate, and now we can go back to our cohomology calculation and use this ui as a correction factor to make our trivialization work. So we define S tilde is Si minus ui. And I mean, then you can, now we should be able to calculate that the differences of these ones on intersection are actually 0. So if all the signs are match up the right way, then we should have Si minus Sj. We can just expand now. So this is this minus Sj minus Uj, and then this and that's okay. And I mean, this is now this up to some sign. So, yeah, no, without changing the sign. And this one, Okay, it matches up. So I was lucky on the 50-50 chance. I mean, you always know how to correct it anyway. If the sign in the end is wrong, you can just change it here. So this is minus here, j. So you have 0. And then you might think, yeah, now it's just a sheaf condition, but it's actually a little bit more complicated. So you now have things on a cover which are equal on intersections, but you don't produce a section of a sheaf, you produce a section of what is called a Porsche, or I mean, we have something with values in a one type. But we can still use some homotopy type theory, so to know that we can patch, but it's more like patching in the stack, maybe. And what does it here in homotopy type theory is Gauss lemma, so let's just leave it like that. Gauss lemma tells us we can glue the SI tilde to some S tilde, which works on the whole of the spectrum of A as a trivialization. And that finishes the proof. So, and I would say this is a lot easier and like kind of makes more sense to me than what you usually do in an introduction to algebraic geometry, where you define the cohomology via derived functors. And I guess to get this one, you need some comparison with check cohomology. And I mean, at least in my basic algebraic geometry, some part of that in the end came out of a black box. Like, and yeah, so yeah, this makes more sense to me. Let's say, yeah, but it might be something different. I mean, yeah, but we'll do that later. Okay, so now, how much time do I have? Yeah, not much.
But I mean, you do exactly the same calculation in
yes.
any.
I mean, this stays the same, but you don't need so much more than this. I mean, the interface around it makes more sense, I would say.
Yeah, I mean, what you prove classically is something like when you have one torsor, one R torsor over an affine scheme, which is locally trivial, then it's trivial.
Yeah, I mean, if you do it like this, then you basically have this proof. But yeah, I mean, that's why I said my basic algebraic geometry first didn't do it like this. But I mean, in principle, you can if you talk about torsors, but then you have to talk about like stacks. I don't know if you get around that. So you have to introduce higher sheaves of some kind.
Well, I mean, as long as we stick to H1,
it's only a 2-1 sheaf.
Yeah, yes.
Only.
Yeah.
Okay, yeah. Okay, yeah, I can do one final thing, which is like realizing what did we actually need from the coefficients here. And what was important is that we can make this calculation, and we can make this calculation because we can pass to algebra and realize that things look like this. So we have this representation from the localized algebras. But other than that, we don't need much specificities from the coefficients. And it turns out we just need a module which doesn't have to be constant. And the module should support this change to localizations. And this is something we call a WQC module, which means weakly quasi-coherent. So, so let M be, say, a dependent module on some type. Sometimes we say bundle of modules in what we write. So, but I mean, yeah, you have a map from X to the type of R modules. So at each point you have some R modules, M little x. And it's called weakly quasi-coherent. WQC. Yeah, that's exactly how I didn't want to make the definition. Let's start pointwise with a module just over R, and we call it WQC if for all elements in R, in the base ranges, we have M localized at R is the same as exponentiating with the proposition that R is invertible. So I'll add that here. So the last one is by definition exponentiating with the proposition that R is invertible. So I mean, first question, are these really modules? Like this one, it's a bit suspicious, but it's just functions. So you have pointwise module structure. And I mean, this proposition, it's two values we kind of understand, like it can be false or true. If it's false, this is trivial model. If it's true, it's like just M, and there's something in between. And there is a canonical map. So you don't really ask for an equality, but for the proposition that some canonical map is an ISO. So the canonical map is ISO. And I mean, the canonical map works by, if you have a proof that R is invertible, then you can kind of eliminate the denominator and produce some element. So, I mean, then it's just R to the minus M times M, which is pure. So, yeah. Okay, and I mean, analogously, we call it M from X to, or let's just say it like this, the type of WQC modules. And I mean, when we want like a bundle of WQC modules, we would just ask for this property pointwise. And yeah, it turns out the theorem holds if instead you say H1 of spec A with values instead WQC modules. So, and yeah, so the proof kind of carries literally over. I mean, at some parts you are more general, but the arguments don't change. So everything we did, you can also do with like a module over R instead of by itself. So I just wanted to eliminate this noise and use that the theory works as a motivation for this definition. I guess so. So yeah, let's meet again at 2. Questions? Yes.
So I'm kind of wondering what's the externalization of these cohomology groups, because I don't know, but in Algebraic geometry we have many different versions of cohomology.
Yeah, I mean, it behaves a lot like just the usual cohomology of quasi-coherent sheaves. You define using injective revolutions and so on. It behaves a lot like this, but I mean, it's generally a very different object, because when you just define this internally, we don't get an external group, but we get a sheaf of groups, like some object in the Zariski topos. So yeah, they might have more information, and it also behaves a bit different. So I will comment on that later. Or it might behave different at some point. So it's not so clear how it compares to the classical thing.
But I mean, so if you change the, say, thinking model-wise, if you interpret all of this in, say, the Ital topos,
then you don't have Zariski local choice. So I mean, the proof doesn't work anymore. But yeah, it could be so. I mean, maybe this is a good general comment. We looked in the beginning at what happens if you work internal in the Ital topos. And I think someone said it already, like it's kind of a trade-off. You get more properties of your base ring, more than local. But for the choice axiom, you get more complicated covers. So, and yeah, we didn't know how to do anything at the point, or at least I didn't. And we switched more to working with other topologies internally. And that seems to work well. And Hugo has worked a bit on doing things with Ital sheaves. Thank you. Okay, so thank you.